Okay, welcome to another validation with Autodesk Inventor Nastran. For this one, I've already built the geometry. It is a 12-inch outer diameter and it has a 6-inch inner diameter. The height is 3 inches. And the only other thing that I've done is I've gone ahead and I've split the bottom face into quadrants. I basically made split lines from 12 to 6 and 3 to 9 so we can leverage that for adding our constraints. So what we're going to do is go ahead and hit environments, and then off of environments we can get into Autodesk Inventor Nastran. And as we go into Nastran, the first thing that I'm going to do is define my material. So just expanding the idealization on the left, double clicking on the material for us. The properties have been defined. The modulus is 30E6 and Poisson's ratio at 0.3. And that's all we need for this static analysis. Go ahead and say OK to that. And I guess next we can add in our constraints. So let's take a look at the bottom of this model. And we're going to go into constraints. And basically what we're going to do is add radial internal pressure. So it's going to push the geometry outward. You can envision that any nodes along the line here between 12 and 6 as my mini axis is oriented. These nodes should move purely in the x direction due to that pressure, so they shouldn't experience any z direction movement. Likewise, anything between 3 and 9, if we give this internal pressure, those should move purely in the z direction, but not x. So that allows me to add some constraints to the model where we can accomplish the constraint that we need without over constraining our geometry. So I'm going to go ahead and select this edge there and that edge there. And like I said, I'm going to leave it fully fixed with the exception of then we know that those nodes shouldn't move in the z direction. So we're going to leave that constrained, but we do want to allow them to move in x. So we'll free that direction up, allowing those nodes to move in the x. Now I am constraining ty. Ty is in and out of the screen. So should the pressure cause this model to contract or expand axially, it's going to do that away from the base of the model, if you will here. Okay. So let's go ahead and say OK to that. And then we're going to add another set of constraints. And again, I'm going to select that edge and that edge. And in this case, we need to allow what? The z direction for that pressure. So we'll say OK to that. So TZ is free there. So we have our constraints. We have the material. We do need to add a load. And for this particular one, it's going to be a pressure. Yeah. And we'll select that inside surface, and it's going to be 1,000 psi. We'll say OK to that. And then our next step would be to generate the mesh. And I haven't gone through this model yet in Nastran. We'll take a look at the mesh. It's pretty good. Maybe I'll just round down a little bit. Let's say we make it 0.5. Again, it's a 3-inch tall. That's probably finer than we need it, but that's OK. All right. So now we have all the basics of our analysis. We have the material, loads, constraints, and a mesh. At that point, we can go ahead and execute the run and see what we get as a result. Taking a look up here, we can see what the number of nodes are and the number of elements. You could see before the analysis started, wasn't a terribly large number, right? So the analysis doesn't take very long. So there's the obviously exaggerated deformed shape of our model. Let's tame that down a little bit. What I'm going to do is right click in the results. I'm going to go to edit, and in here we'll go deform options, make it actual. That's good. You can exaggerate it. We can make it 10 times or 100 times the actual, but that looks good to me. let's first check our displacements, and we're going to check in one of the directions. Let's say either X or Z. They should be the same, just opposite in sign on either side of the model. So there we go. We can see a max value there of 1.962 e to the minus 4 or 1.963 e to the minus 4 at the opposite end. So this example comes from Rourke and Young, page 504, table 32, case 1A from the 5th edition. So let's go ahead and type in what our displacement is here. So it's 0.0001963, and we'll see what percent difference we get. We get 0.2%, so not even 1% different from the book. And then the other thing that we're going to check is a stress, and they are giving us a hoop stress. So to accomplish that without doing a local coordinate system, what we're going to do is also take a look at stress, our tensor either in the x direction or the z direction. Again, they should be equal, just opposite, where they occur on the model in each quadrant. So let's go ahead and take a look at stress. And there's our x. And we're seeing a value of 1669. Right, and let's take a look at Z. We'll take the worst of the two values, 1669, and in Z, oh yeah, that's pretty good one there. So 1684 is what we see in the Z. Let's use that one. 1684 was it? Basically, 1684, and that gives us a percent difference of just over 1% different than what the hand calculation would come out to be. So I think all in all, pretty good validation. And again, I enjoy doing these. We know what the solution should be from the text. We have reference there about what the dimensions of our geometry are, what the loads are, the theoretical results, and we can compare and make sure that the program is doing what we want it to do. And in this case, certainly looks like the program is working just fine here. Thanks for watching.